And look at chapter 7. Chapter 7 is probably one of the easier chapters because it deals with two things that you are physically aware of. Well, actually, three things. You're very much aware of clouds. They are the only visible part of weather that you can see, and precipitation. Okay, that goes without saying. You can see it snow, you can see it rain. The other part of this is humidity. And humidity is going to run whether or not you have clouds and therefore have rain or snow. So the chapter first starts looking at the breakdowns of water, where they are on the planet. There are some percentages and things like that in the notes. I am not going to hold you responsible for the percentages. I just wanted you to know the breakdown of where water is, and that most of the fresh water on the planet that we utilize for drinking water, fishing, and the hydrologic cycle is limited to less than 2% of the entire amount of water on the planet. One of the first things that you notice in the chapter are the phase changes. And again, a phase change is anytime water will change from one state of matter to another one. So we know water has three states of matter. It has a liquid phase, a gas phase, and a solid phase. The difference between all these phases is going to be temperature, either increase of temperature or decrease of temperature. So one of the first ones and easiest ones to understand, of course, is evaporation. Most everybody understands evaporation. Evaporation is going to be where liquid water is going to turn to a gas, and in order to do this, you have to increase the temperature. What you might not understand is that the increase of temperature does not have to be to its boiling point. Water, if you cook it on the stove in a pot making spaghetti, you're going to see steam, and that's going to start happening when the water gets somewhere up to 150 degrees. When it starts to boil at 212 degrees Fahrenheit, then you're changing and you're getting a lot of steam, and that's changing liquid water into a vapor. You know, on the planet, we can't do that. We can't go from 30 degrees to 212 degrees to get moisture into the atmosphere. But if you warm up the air, warm air always has a higher rate of absorption than colder air. That's why the summertime is more humid and why the wintertime is always dry. So evaporation is going to increase temperature, and the liquid is going to eventually turn into a gas. Condensation is the flip of that. If you want to bring the gaseous moisture, the humidity, and condense it and turn it into a liquid, you have to lower the temperature. So in order to do this, the gas is going to have the molecules slow down. So imagine you have a drinking glass out on the table this summer. You have ice cubes in it, your drink's somewhere around 40 degrees, but it's a 95-degree day outside. The air going across is 95. The air in around that glass is closer to the 40, 45 degrees of your drink. So the air temperature is going to cool down, and when you cool that down, the molecules slow down, they coalesce, they stick to the glass, and they turn into liquid. Okay, so condensation occurs. You don't have to worry about putting out coasters very much in the wintertime because the air is so dry. If anything does condense, it evaporates and turns into a gas anyway. Glaciation. If you look at that word, you see the word glacier basically in it, and glaciers are ice. So you're going to turn liquid into to a solid. And in this case, you're going to drop the temperature below 32 degrees Fahrenheit or 0 degrees Celsius. Sublimation is the one term out of those four that you probably haven't heard of, and if you have, it was sparingly used. Sublimation is kind of a strange process. It takes it from a gas and sends it up into the atmosphere and turns it directly into a solid, but without becoming a liquid first. It doesn't go from a gas, then a liquid, and then a liquid to a solid. It doesn't take three steps. So my diagram is this. You've got the sun. The sun is going to heat up the ground. Terrestrial radiation is going to start to release heat. The heat is going to go through the process of convection, which is the vertical movement of heat. The gas molecules, which you can't see in vapor, are going to be taken from the ground level and all the way up into the higher levels of this cloud. Now, the bigger the clouds, we're going to learn this a little bit later in this chapter, the larger the clouds, the more convective power they have, the more suction they have. Imagine these clouds, or the taller the clouds, it's like a big vacuum. The bigger the cloud, the bigger the vacuum. The bigger the vacuum, the more volume it can take up in its suction power. So it's going to take these gas molecules and it's going to take them directly up into upper parts of the atmosphere, which is past the freeze line. This area of the cloud will be cool, but maybe not enough to turn it into ice. But even in the summertime, you're going to have heights of these clouds that when moisture is taken up, it's going to be below 32 degrees Fahrenheit, and it's going to turn directly into a solid. So this turns into an ice crystal up here. This process in the summertime, it can happen, well, it happened this year in probably mid-spring to late spring because we had such an abnormally warm spring. It was cool here, but it was still wintertime up here because it hadn't transitioned into summertime yet. So the temperatures in the middle layers of these clouds are going to be very cold. Even now in the end of June, it's going to be very cold up here. So the air temperature is going to delegate what this molecule is going to turn into. So below 32, it's automatically going to freeze, even though it was a gas. So this ice crystal is going to be created, and since it's turned to ice now, it's going to be heavier than gas, and it will probably start to drop, and then more convection is going to push it back up. It's going to refreeze, and it's going to be heavier. It's going to keep dropping. It's going to bounce back and forth. And what sublimation really creates, this is how hail is created. Hail is created because gas is going to be pulled up into the atmosphere. It's going to turn to a solid. It's going to get heavy. It's going to drop. Air is going to push it back up. It's going to refreeze it. It's going to drop. It's going to push back up, and it's going to keep doing this like a ping pong ball. Once it gets too heavy for the cloud's convection, then it will fall out of the cloud as a hailstone. Okay, but we'll look at hail at another date. The other thing that we want to look at within this chapter is the terminology. And this is one of the things that does get a little bit confusing. Okay, when you watch the news and you watch the weather, they talk about humidity. Okay. Humidity is just basically moisture in the atmosphere. It's a general term. Okay, you can't see it, you can feel it. There's going to be times, especially this time of year, if you've ever been driving around, especially late afternoon, early evening, and you see what looks like fog over a cornfield, or if you wake up early in the morning and you're driving down the road and there's a pond and it looks like there's smoke on it. You can see the moisture. Okay, this is humidity. Humidity is just a generalized term for any moisture that you find in the atmosphere, and it's typically going to be in gas form. Humidity is broken down into two aspects. You have what's known as absolute or specific humidity, and this is the actual amount of moisture at the time that you're studying it. This is usually given to you in the form of grams per cubic centimeter, or which is known as cc's. You can also look at it in amounts in inches. But absolute or specific is designed to help us figure out the other kind of humidity, the one that most of us listen about. You can go out and take a hygrometer. There are little handheld machines that are about the size of a cell phone, and it has a probe on it. You can walk outside, the probe will read how much moisture is in the air in that parcel at that time. Okay, that's an actual amount. So then we can figure out dew point and saturation levels from there. Okay, this is important because when you start looking at dew point and frost point, this helps determine how soon it's going to rain, or if it's going to rain at all. Okay, dew point is telling you the amount of moisture that's in the air. How much can the air hold, and how much is there right now is relative humidity, and that helps determine dew point. Well, let's look at the second one. The second one is known as relative humidity. Relative humidity is basically an equation. It is the actual amount, which is what we just learned up here, the specific, divided by the capacity times 100. So we're going to look for relative humidity is equal to the actual amount of moisture that we have, whatever we found out when we took the hygrometer outside. We know what every temperature of air, how much it can hold, that's the capacity. So you divide those two things out, you multiply them by 100, and you get a percentage. So when you look at your weather bug or the weather statement, it will tell you humidity in percent. It'll say it's 85% outside. What that tells you is that 85% of what the air can hold is there. So 85% humidity is pretty humid. You will notice as you breathe in right now, it feels like it's very heavy. And that's because there's a lot of moisture in the air. As the temperature cools down, you will start to see that the humidity level percent will go up. As the temperature drops, if we have 10 cubic centimeters in there right now, and that creates 85% humidity at 90 degrees, If we pull the temperature down 10 degrees to 80 degrees, now we're looking at probably close to 100%. You will probably have rain, or at least fog at that point. Okay, so relative humidity is used to determine, like I said, help determine dew point. Dew point and frost point. Those two temperatures are also very important. Okay. Dew point and also frost point, they are basically the same thing except for the temperature. It's the temperature at which air is saturated. Dew point is going to be above 32 degrees Fahrenheit, and frost point, of course, is going to be below 32 degrees Fahrenheit, because frost has to come when you go through glaciation. Okay. Here's the thing about dew point and frost point. The dew point temperature and the air temperature are two things that you can look at on weather information. When you pull up weather information on the computer or on the internet, it's going to tell you what the actual air temperature is. So if the air temperature today is 85, but the dew point temperature is 81, is it possible for the temperature today to drop 4 degrees to reach this? Is that unheard of? No, it's only 4 degrees. That could happen within a few minutes, right? We have a cold front move in, the wind starts picking up, we can drop. You will notice if these two are like that, that your relative humidity is probably 95% or higher. When this is at 95, and when you get this number, relative humidity close to 100, that's when you're going to start having precipitation. So if these two temperatures are relatively close to each other, your humidity level is usually pretty high. That means there's a really good chance you're going to have precipitation. If we look at this and the dew point temperature is 67, is that something that's going to happen or change within a few minutes or a couple hours? Probably not. Now, could it happen during the evening? Yeah, we could drop from 85 down to 67 at this time of the year. That's not unheard of. But the further apart these two temperatures are, the less likely you are to have precipitation. Okay. So remember, I said in the last chapter to check out air pressure. So if your air pressure gets below 30, as it goes 29.99, gets down to 29.9, 29.8, your chances of precipitation start to increase. You will also notice that your cloud coverage increases, the air gets more humid, the temperature is going up, and so on. But these are the numbers that you look at when we refer to humidity and precipitation. If these two numbers are really close, the dew point temperature and the air temperature, you're going to be in a high percentage chance of having some kind of precipitation. But always check your relative humidity. In the morning, it's usually going to be pretty high. As the air gets warmer, it's going to accept more moisture. The humidity level will drop. It will not drop, though, if these two temperatures are close to each other. It will stay relatively high. If you have these two close together and a high percentage of humidity early on in the day, there's a pretty good chance you're going to have rain or a thunderstorm in the short future. Okay. I'm going to stop here. I'm going to bring you back. We'll break down clouds and fog in the next segment, and that should be the end of this chapter.